Hi everybody, Assalamualaikum and salam sejahtera to all. So I think it is not too late for me to wish you Selamat Hari Raya and Selamat Hari Gawai. Hopefully everybody's doing fine and happy with your family, especially during this festive season. Okay, so now we go back to reality and continue with topic 5, numerical integration, and with Simpsons one-third rule. Okay, at the end of this lecture, you should be able to derive the formula for Simpsons one-third rule of integration, and then use Simpsons one-third rule to solve integrals in civil engineering problems, and then develop the formula for multiple segment Simpsons one-third rule of integration, and lastly, using multiple segment Simpsons one-third rule of integration to solve integrals. So now we will look at what is the Simpsons one-third rule. Okay, so the Simpsons one-third rule is when a second order interpolating polynomial is substituted into the integration equation of function x. So if a and b here are designated as x0 and x2, and f2x is represented by a second order Lagrange polynomial. So this is the second order Lagrange polynomial. Okay, so after integration and algebraic manipulation, the following formula will result to equation 5.17, which is I equal to h over 3 multiplied by fx0 plus 4 times by fx1 plus fx2. Where for this case, h is equal to b minus a divided by 2. If we could refer to figure 16 in the lecture notes, there's an alternative derivation shows where the Newton-Gregory polynomial is integrated to yield the equation of this integration, which is h over 3 multiplied by fx0 plus 4fx1 plus fx2 minus with 1 over 90 h power of 5 and a fourth derivation of xi. So this part of the equation of the integral equation is actually the Simpsons one-third rule, which if we substitute the value of a, b and x1 into the equation, we will get this general equation for the one-third rule, Simpsons one-third rule. And the other part of the integration equation is actually the tangential error of the Simpsons one-third rule. That is denoted by ET equal to negative b minus a power of 5 divided by 2880 multiplied by fourth derivative of the xi. Okay, since the b value is substituted with b minus a divided by 2. So now we will look at example 4, which is for single application of Simpsons one-third rule. Use the single application of Simpsons rule to integrate the equation of or the function of 0.2 plus 25x minus 200x squared plus 675x cubed minus 900x power of 4 plus 400x power of 5. So from A to B and estimate for the error. Recall that the exact value of the integral is equal to 1.640533. So for the solution, we will substitute the value of x into this equation. Okay. So when x equal to 0, fx equal to 0.2, and x equal to 0.4, then fx equal to 2.456, and 0.232 when x equal to 0.8. Therefore, substituting all this value into the integration equation, we will get I equal to 1.367467, which can be represented to error of, okay, this is the z value of the integration, minus with the estimated value coming from one-third rule or Simpsons one-third rule, and we will get the true relative error equal to 16.67%. So the estimated error is, or the truncation error, equal to negative b minus a power of 5 divided by 2880 multiplied by fourth derivative of the share. So when we substitute all this value inside the equation, where previously we get fourth derivative of share equal to negative 2400, then we will get the estimated error equal to 0.2730667. Okay, now we will go to the multiple application of the Simpsons one-third rule. So just as with the trapezoidal rule, as shown in the figure here, okay, Simpsons one-third rule can be improved by dividing the integral interval into a number of segments of equal width, which is h equal to b minus a over n. So as illustrated in this figure, an even number here, an even number of segments. So even number of segments must be utilized to implement the method. So for this method, multiple Simpsons one-third rule, the number of segments must be even. Alright, okay, so the total integral can be represented as this equation. Okay, the summation of integration from x naught to x2 plus x2 to x4 and so on until x1 minus 2 xn. Then substituting the Simpsons one-third rule for the individual integral will yield this summation of the integration for the whole segment. Alright, so the summation of the integration equal to the individual integration for the first integral plus with the second integral and so on until the n integral. Okay, or the terms can be combined as below here. So the general equation for the integration for multiple application of Simpsons rule equal to b minus a, which is the width of the segments, multiplied by fx naught plus 4 times by the function for the odd points, which is 1, 3, 5 and so on, and then plus 2 multiplied by the function at the even points, and plus fxn divided by 3 multiplied by the number of segments. So all that is the average height of all the segments. Okay, so the estimated error for the multiple application Simpsons rules can be obtained by this equation, which is EA equal to negative in bracket b minus a power of 5 divided by 180 times by n power of 4 multiplied by the average fourth derivative for the interval. Let us look at example 5 for the multiple application version of Simpsons one-third rule. Okay, for n equal to 4 or a segment's number of 4, use the multiple application of Simpsons rule to integrate this equation, which is similar from the previous example. So integrate this function from a equal to 0 to b equal to 0.8 and then estimate the error. Recall that the exact integral is equal to 1.640533. Okay, for the solution, since we have a segment number of 4, then we will have 5 number of points. Okay, this is obtained from dividing this b minus a with 4 with the number of segments. Okay, so and then substitute all the points value inside this equation to get the individual values for the functions. So for example here, the point naught, okay, so f0 equal to 0.2, and then for the point number 1, f0.2 equal to 1.288, and point number 2, okay, 0.4 equal to 2.456, and point number 3 and point number 4. Alright. So therefore, by substituting all this value inside the general equation for the integration, which is 0.8 multiplied by the function of x naught, okay, plus with 4 multiplied by the function at odd points, okay, which is 1 and 3, plus with 2 multiplied by the function at the even point, number 2, and plus with the function at the nth point, or 4 point, okay, 0.232. Then divide by 6, then we will get 1.623467, which will represent a true error of, okay, so this is the exact value of the integration minus with the estimated value, okay, then we will get 0.017067, okay, bringing the relative true error equal to 1.04%. Alright, while for the estimated error, or the truncation error here, is equal to negative 0.8 power of 5 divided by 180 multiplied by 4 power of 4, okay, and multiplied by negative 2400. This is the fourth derivative of the function. So we will get 0.017067. Okay, for the next topic, in topic 5, for numerical integration, is the Simpsons 3-8 rule. At the end of this lecture for the topic, you should be able to derive the formula for Simpsons 3-8 rule for integration, and then use the Simpsons 3-8 rule to solve integrals in civil engineering problems. Then use multiple segment Simpsons 3-8 rule for integration to solve integrals, and combine the Simpsons 1/3 rule and Simpsons 3/8 rule to approximate the integrals. So for the Simpsons 3/8 rule, in a similar manner to the derivation of trapezoidal and Simpsons 1/3 rule, a third order Lagrange polynomial can be fit to 4 points and integrated as this. Okay, the integration of function x from a to b. And then to yield this equation, okay, I equal to 3h/8 multiplied by fx naught plus 3fx1 plus 3fx2 plus fx3. Okay, this equation is known as Simpsons 3/8 rule because h is multiplied with 3/8. Okay, it is the third Newton Cotes closed integration formula, and the 3/8 rule can also be expressed in the form of this: I equal to b minus a, which is the width of the segments, multiplied by fx naught plus 3fx1 plus 3fx2 plus fx3. Okay, thus the two interior points are given width of 3/8. So this one is the interval points, and the end points are weighted with 1/8. So this is the 8 points. So the Simpsons 3/8 rule has an error of ET equal to negative 3/80 h power of 5 and multiplied by fourth derivative of xi. Since h equal to b minus a divided by 3 for this rule, so the error can be simplified into this equation. Alright, et equal to negative in bracket b minus a power of 5 divided by 2880 multiplied by the fourth derivative of xi. So note here that the denominator is bigger than the Simpsons one-third rule, so that somehow this rule, the Simpsons 3/8 rule, is more accurate compared to Simpsons one-third rule. Okay, usually the Simpsons one-third rule is the method of preference because it attains third order accuracy with 3 points. Alright, so this one is the one-third rule. Rather than the 4 points required for third 3/8 rules. So for the 3/8 rules, it requires 4 points. 1, 2, 3, 4. Okay. But the 3/8 rules has utility when the number of segments is odd. Okay, number of segments is odd. For example, for this one, there are three number of segments. While for Simpsons one-third rule, the number of segments is 2, which is even. Okay, so an alternative would be to combine these two rules, so that in this way we could obtain an estimate with third order accuracy across the entire interval. So now let us look at the example 6 for the application of Simpsons 3/8 rule. Alright, use Simpsons 3/8 rule to integrate the function here, which is similar with the previous example, from a to b, estimate for the error. And recall that the exact integral is 1.640533. And then b, use it with conjunction with Simpsons 1/3 rule to integrate the same function for 5 segments. Okay, so that means you need to combine the Simpsons 1/3 rule, 1/3 rule, and Simpsons 3/8 rule. So for a single application of Simpsons 3/8 rule requires 4 equally spaced points. All right. So we have here functions with different values of points, which is 0, 0.2667, points number 1, 0.533, points number 2, and 0.8, points number 3. So this one is point node, point 1, point 2, point 3. Okay, so substitute the values inside the general equations of integration. I 0.8 multiplied by 0.2 function at x node, plus 3 multiplied by the function at points number 1 and number 2, plus function at points number 3, 0.232. So divide by 8, then we will get 1.519170. And then we will obtain the true error, okay, by minusing the approximate integration from the actual value of the integration. So you will get 0.1213630 and the relative true error of 7.4%. And then the estimated error or the truncation error is here, 0.8 power of 5 divided by 6480 minus with negative 2400. Why? Okay, next, for the question B, we need to combine the Simpsons 1/3 rule and Simpsons 3/8 rule. So the data needed for a 5-segment application is 5 number of points. Okay, So here we have x naught, fx0, and then we have x1, fx x equal to 0.16, and then fx2, fx3, fx4, and fx5. Okay. So the integral for the first two segments is obtained using Simpsons one-third rule. Okay. I equal to 0.32, which come from b minus a, which is b is point number 2 minus with point x naught, and then multiply by 0.2 fx naught plus 4 times by fx1 plus 1.743393, which is fx2, divided by 6. Then we will get 0.3803237. Okay. And then for the last three segments, the 3/8 rule can be used to obtain this integration. Okay. I equal to 0.48, which is obtained from 0.8 or the point of fx5 minus with the point of fx2. 0.8 minus 0.32. Okay, multiply by 1.743393, which is points number 2, plus 3 multiplied by internal point number 3 and number 4, and plus the endpoint, which is fx5. Okay, number 5, 0.232 divided by 8, then we will get 1.264754. So the total integral is computed by summing these two results. Alright, so this is the total integral. And then after that, we can determine the true error of the estimation. So here we get negative 0.00454,383, yielding to the relative true error of negative 0.28%. Okay. Okay, for the other example of combinations of rules, example 7, a river was studied for 3 different parameters, namely distance, y, depth, h, and velocity, u. So 6 data points were collected as shown in the table for all 3 parameters respectively. Compute the cross-sectional areas and its flow rate using any numerical integration method. So now we're trying to use the combination of rules to solve this equation. So for the solutions, the cross-sectional area can be evaluated using a combination of Simpsons one-third rule and the trapezoidal rule. So here, the first 3 points, which is from 4 to 0, or 0 to 4, is using the one-third rule, the Simpsons one-third rule. And then the next 3 points from 4 to 6 is also using the Simpsons one-third rule. And the rest, the last 2 points, is using the trapezoidal rules. Alright. So by summing all the integrals, we will get the cross-sectional area equal to 9.525 meters square. A table can be set up for the values that are to be integrated for the flow rate. So we calculate the UH from the table given in the question, and then integrate for the flow rate. So note here that it's similar to the cross-sectional area method. So for the first 3 points from 0 to 4, we are using one-third rule. And then the second 3 points from 4 to 6 is also using one-third rule. And then the rest of the 2 points. It's calculated using the trapezoidal rules. Trapezoidal. And in the end, for the summation of flow rate, we will get 0.7617 meter cube per second. So that's all for the topic 5.2, Simpsons rules, which consists of Simpsons 1/3 rule and Simpsons 3/8 rules. Thank you.